Good afternoon, ladies and gentlemen. So, welcome to the this last topic for today and for this exhibition. So, I'm going to tell you about the devulcanization or rubber recycling. But this is a bit deep research about the effect of fillers in devulcanization. So, this work is a collaboration between Prince of Songkhla University, Pattani campus, Thailand, and Department of Elastomer Technology and Engineering, University of Twente, the Netherlands, and also Rubber Research Institute of Malaysia in Malaysia. So this work is all contributions from 3 countries. First of all, if we look about the rubber, of course, the rubber products is a very a tough material to do the recycling because they have a 3-dimensional network in the rubber. So it is difficult to do the recycling it. And especially with tires, because in tire they compose of many types of rubber and also fillers from many parts of tire. So to do devulcanize it or do recycle it is very complex. Then let me introduce a little bit about how to recycle tire. So actually we have these recycling steps of tire recycling. First is energy recovery, is burning used tires for energy recovery, and this is the lowest method to do the recycle. And the next step is back to the feedstock, is pyrolysis, the used tire for recovery of oil, gas, or chemical. This is the next and the better step of used recycled tire. But the better and the best one is material recycling, and this is the best one. So what is that? Is that to recover used tire in new rubber products. For example, we have tire and then we grind it and use it again in the rubber products, use it as a rubber materials. And also, if we, the best one that I told you in this ladder is the from used tires to new tires, is that, for example, if we have the tire and we do recycle it, and finally we can put this recycled rubber in tire again. And this very, very difficult to do that. But of course, we have done some research and some experiments that we can put some recycled rubber in the new tire again. And this is also some research about to use this recycled rubber in tire. Okay, why this is very difficult to recycle used tire? Because when we have a 3-dimensional network here, this is a model of a rubber molecule. When we do vulcanize it, so we link the molecule together with sulfurs, and the blue one is sulfur, and then we link it, make it a network of rubber. And this is very difficult to use it again because it's become to be a network. When we want to use it again or we want to recycle it, we have to break this network, to break it. But here you can see that we break at the blue points at the sulfur bridge that we tiled it before. But actually, in the real life, we cannot do it just like this because the main molecular chain will break also. Then when the main molecular chain here is break, the recycled rubber will have a lower property than the normal rubber because this we get a short chain molecules. So what we have to do and what we want to do is do devulcanization. That what we want to reverse the reaction of vulcanization. That is, we want to just cut only at the sulfur bridge. So we call this process, this recycling process is devulcanization. Okay, we have done the research and published some results already. with the tires rubber. So in tire, actually we have many types of rubber in there. Here is a passenger car tire. They have styrene butadiene rubber, so SBR, butadiene rubber, BR, natural rubber, NR, and also butyl rubber or IR here. So we simulate the models of this kind of rubber. We cure it and we do devulcanize it. The devulcanization that we use is we use thermochemical devulcanization conditions that we have here, the temperature of 220 degrees C, and we use this DPDS, diphenyl disulfide, as a devulcanization aid with 5% of TDE oil. And of course, the nitrogen gas atmosphere can help us to avoid from the oxygen. And also after we get the devulcanized rubber, we dump it into the liquid nitrogen. And we also have tried many parameters to have looked if this can affect on our devulcanized rubber properties. So first, we have tried many types of devulcanization aid here, and the devulcanization temperature is varied from 180 to 300 degrees C. And we also use the thermal stabilizers to do the radical scavenger in the process. And also, we try the devulcanization condition in air and also in nitrogen atmosphere. Okay, after we do preparation of the devulcanized rubber, we have to check if our devulcanized is doing well. So we do check the devulcanization efficiency or from testing the rubber soluble fraction and the cross-link density. So let me elaborate a little bit about this. So the analysis is that we have a devulcanized rubber here, and then we extract it with the acetone to remove some polar chemicals such as the accelerator or devulcanization aids out, and then we follow by extract in the THF, and then to remove oil and also the soluble rubber. Then we can have the soluble rubber, then we calculate the percentage of rubber sol fraction. So, and the leftover part is the gel fraction. We do check the cross-link density of the gel fraction. And this is a bit complicated, and we need a mathematical theory to understand the devulcanization efficiency. Actually, it is we call Horrocks. If you type to the Google, and then you can find the Horrocks plot. It's the plot that to understand about the relationship between the soluble fraction and decrease in cross-link density. And you can have a rough to know that your devulcanized rubber is going to the proper way or not. So from these two equations, we can have these two lines. The first line is the black lines here is the random scission. The meaning is when you cut the network without any selective position. For example, you cut it at the sulfur bridge and also at the main molecular chain. You can cut it everywhere, so you get the data point go to these lines. But if you can selectively cut at only at the sulfur bridge, your data point will go through this dot line. So this is the theoretical this is just the theoretical developments. Okay, so to go a little bit details. For example, here we cut this rubber network and we cut only 2 points, and then we can get some soluble rubber. You see here, you cut only 2 points, then sol rubber is come very early stage. And here, if you see at the black lines here, you can see that the sol fraction is go very fast, even you cut just a little bit. But if you, for example, want to cut only at the sulfur bridge, I assume here is the red spot. If you cut only the sulfur bridge, then the loose chain also come, but you have to cut many times. Then you can see here that you have to decrease a lot of cross-link density. Then you can get the soul fraction. So this is the meaning of these two lines. But okay, it is very a bit complicated that I can tell you this long story for a very short time. But this actually I myself have to study it for a year to understand this line. But I try to speak very briefly to you. Okay, for this is the results that we try with the SBR rubber. We use these two temperatures. This is 220 and 260. We have our data plot at very close to the line of the cross-link scission. That means that with our this condition, we have the very successful or efficient devulcanization, but only 70% decrease in the cross-link density. What we have found, another one is when we increase the temperature from 220 to 260, we can see that the data point is go to the left-hand side. That is, the meaning is that it is inefficient occur. So it means that when we increase the temperature, it's not a good way to do with the recycling. Okay, here if we have the normal vulcanized rubber, we will start with in this point. And also if all the chain are loose from the network, this we can go to the end of this curve. We have tried in the same method with the BR, NR, and also butyl rubber. And this is the position of these rubbers. That is, for BR, it is located at the black lines. For butyl, even worse, that is go to the left-hand side. But and fortunately, for natural rubber, it's easy to do the devulcanization or do recycle because it's go to the end of the process. So if you recycle or devulcanize the natural rubber, it's not that difficult. You can do it very not that difficult. But especially with the tire, if you go to the truck tire or the tire that you are sure that is from natural rubber, it is not much difficult. But if you are doing with the tire that composed of a lot of rubber, for example, the passenger car tire that have also the SBR, BR, and other synthetic rubbers, so the story is a bit complicated. Okay, we have used this condition in a real used tire from passenger car tire, and what is found is the data points is plotted at very left-hand side, and also just only 30% of decrease in cross-link density. That is our big problem because what we expect the data points is go to the right-hand side, but what we found is just a beginning. So this is our problem because we have inefficient devulcanization. So why is that? What we thought is it may because of in the tire they have a lot of type of rubbers, and also the fillers. We have also carbon black and sometimes silica. So this is make this thing more complicated. Then in this study we think about that, and when we go to the filler first, that we think that the filler in the rubber may affect on our devulcanization. Then our objective is to study the influence of carbon black types and also loading on the devulcanization efficiency in single tire rubber. So we put the carbon black on this formulation of each rubber. For example, we have SBR formulations here, and then we vary the amount of carbon black from 0, 30, 60, and 90 phr. And also we have do the same methods for the NR, BR, and also butyl rubber here. And we have a look about the devulcanization efficiency. We use the devulcanization condition as same as before. This is DPDS, TDE as a devulcanization aid, and oil. The temperature is 220 and with nitrogen gas purging, and dump it in the liquid nitrogen. And what we have found that when we increase the, for example, this is SBR, when we increase the carbon black, we use these two types of carbon black is N330 and N550 is from the bigger size and the small size. And for example, here we have N330 of carbon black 30 phr. And when we increase the amount of N330, so we can see here that our data points is go to the left. Yeah. And also when we increase to 90 phr, is go to the more to the left. This is found also with the N550 that we start from here at about 50% of decrease in cross-link density, and then we increase to 60 phr, is go to the left-hand side, and for 90 phr also. And that we found is as well with the BR rubber in the same trend. But for natural rubber, what we found is still at the end of the vulcanization process. That means this process is work well with the natural rubber. However, we found also with increasing the amount of carbon black, the cross-link density of natural rubber is going a little bit to the left. Then I'm going to conclude my research work in this time that carbon black loading affects the vulcanization efficiency. However, varying carbon black particle size show no effect on the devulcanization efficiency. And also increase of carbon black loading results in an increase of cross-link density in the synthetic rubber, however decrease of the cross-link density of the natural rubber. Okay, I would like to thank all the contribution in this work, and also thank you for your kind attention.